A equals Q times lam times Q-transpose. This is not just a formula, it is a recipe for revealing structure. Q-transpose rotates your data to its natural axes. Lam scales each axis by its eigenvalue. Q rotates back. Every spectral method in machine learning, PCA, ZCA whitening, spectral clustering, kernel PCA, follows this exact pattern. The eigenvalues tell you how important each axis is. The eigenvectors tell you which direction each axis points. Today we implement the complete workflow, from raw data to projection to reconstruction error. The decomposition A equals Q lam Q transpose holds when A is symmetric, meaning A equals its own transpose. Covariance matrices, gram matrices, and graph Laplacians are all symmetric. Q is an orthogonal matrix, its transpose equals its inverse. Columns of Q are the eigenvectors, they form an orthonormal basis. Lam is the diagonal matrix of eigenvalues. Non-zero off-diagonal elements of A become zero in the Lam representation. That is what diagonalization means. For the covariance matrix sigma equals 4, 2, 2, 3, eigenvalues are 5.56 and 1.44, summing to 7 equal to the trace. For non-symmetric matrices, use SVD instead. PCA has 6 steps, memorize them. Step 1. Center the data by subtracting the column means. Step 2. Compute the covariance matrix as X-centered transpose times X-centered divided by n-1. Step 3. Eigendecompose the covariance matrix with NP, linear LG. A use A not EIG, it is faster and returns real sorted eigenvalues. Step 4. Reverse to descending order since A returns ascending. Step 5. Project by multiplying the centered data by the top k eigenvector columns. Step 6. Compute explained variance ratio as each eigenvalue divided by the sum of all eigenvalues. The cumulative sum tells you what fraction of total variance your k components capture. 4 applications. 1. PCA for dimensionality reduction. Top k eigenvectors of the covariance matrix capture maximum variance. Use sklearn, decomposition, PCA or implement manually in 6 steps. 2. ZCA whitening. Use the full eigendecomposition to transform data to identity covariance. Unlike PCA whitening, ZCA preserves the original feature orientation important for image data where spatial structure matters. 3. Spectral clustering. Eigendecompose the graph Laplacian. The Fiedler vector, the eigenvector for the second smallest eigenvalue, partitions a graph into 2 groups. Apply k-means to the first k eigenvector rows. 4. For your 96,000 device monitoring network, build a metric correlation graph, compute its Laplacian, and eigendecompose to find natural device failure clusters. 3 patterns. First, projection and reconstruction. Project to k components with z equals x-centered times q top k. Reconstruct with x recon equals z times q top k transpose. Reconstruction error is the mean squared difference between x-centered and x-recon. Second, scree plot. Plot the explained variance ratio for each component. The elbow where the curve flattens is typically the optimal k. 2 components capturing 70% of variance is usually a good trade-off. Third, which function to call. A for symmetric matrices covariance, gram, Laplacian. SVD for any matrix including rectangular feature matrices. e.g. only if the matrix is not symmetric it may return complex numbers. One formula to know cold equals Q times lam times Q-transpose. Q rotates. Lam scales. Q-transpose rotates back. For PCA, 6 steps: center, covariance, A, sort, project, compute explained variance ratio. For symmetric matrices, always A. For rectangular data matrices, SVD. Reconstruction error measures how much information you lost. 2 exercises. Implement all 6 PCA steps from scratch on random data. Then compute reconstruction error for k equals 1, 2, 3, 4 components and verify the error decreases monotonically. You now have the full eigendecomposition toolkit, the formula, the intuition, the PCA workflow, ZCA whitening, spectral clustering, and the AIOP's application. Video 14 is singular value decomposition, the generalization of eigendecomposition to any matrix shape, including your feature matrix X, which is n samples by n features and never square. SVD is the foundation of modern NLP word vectors, collaborative filtering in recommender systems, and image compression. It is where this entire module has been pointing. Subscribe so it is ready. Post your 6 PCA steps in the comments. See you in video 14.